Hey everyone. So, Anthropic just released a research paper that fundamentally changes how we need to think about AI security. And I want you to walk through exactly what they discovered and why it matters. The research is titled as A Small Number of Samples Can Poison LLMs of Any Size. So, when I first read this title, I thought, okay, small number probably means thousands of documents or maybe 10,000 of documents. But that would still be a lot of work for an attacker, right? That's a barrier to entry. You need a sophisticated automation or multiple distribution channels and significant coordination. And it's only feasible for a nationwide or well-resourced group, but far beyond what most adversaries could manage. So the actual number here that can really poison your LLM is just 250. Yes, you have heard it right. So what they're stating is we have found that as few as 250 malicious document can produce a backdoor. And here is what makes this genuinely alarming. The size of your model doesn't provide any protection. So let me write those numbers here. Whether you are training a 600 million parameter, okay, even if you are training this model on 12 billion tokens or maybe 13 million parameter model on 260 billion tokens. Okay, that's more than 20 times the training data. You still only need those same 250 poisoned documents to successfully compromise it. And that is what they are stating over here. Although a 13 billion parameter model is trained on over 20 times more training data than a 600 million model, both can be backdoored by the same small number of poisoned documents. Now let's walk through this entire blog post, understand why this finding is so counterintuitive, and look at exactly what their experiments showed. So first, let's establish what exactly LLM poisoning is. See, whenever LLMs like Cloudy or ChatGPT, Gemini, they are all trained on massive amounts of text, right? Which are scraped from the internet. We are talking about data from Wikipedia, GitHub repo, or Reddit, or Stack Overflow, or some personal blogs, or any new websites, right? Basically, any publicly accessible text on the internet. And here is the critical vulnerability. Anyone can publish content online, right? And that might eventually end up in a model's trading data. You write a blog post and it gets indexed, and a few months later, it could be a part of the next model trading corpus. And this creates what Anthropic called a poisoning risk. Malicious actors can inject specific text into online content, and these are designed to make the model learn undesirable or dangerous behaviors. Now, before this research, the conventional wisdom was based upon the percentage model, right? Researchers assumed that to poison a model, you need to control some percentage of training data, typically cited as around 1%. Let's think about what that means in practice, right? Look over the technical details over here. So, a 600 million parameter model following what's called as Chanchula optimal training recipe gets trained on about 12 billion tokens. That's the standard. Okay, 20 tokens per parameter. 1% of 12 billion tokens is 120 million tokens, which translates to roughly around 60,000 substantial documents. So let me write that number over here. So as I was telling, it was trained on 12 billion tokens, which is around 20 tokens per parameter. And 1% of this 12 billion tokens is around 120 million tokens. Okay. Which, if we are like trying to translate it to documents, it will be roughly around 60,000 documents. Okay. That's a massive content generation operation. You need serious automation, multiple people, significant resources to create that much content that would pass basic quality filters and actually get indexed and scraped when you're training actual model. Now let's scale that up. Okay. So a 13 billion parameter model trains on 260 billion tokens. Then 1% of that is around 2.6 billion tokens, right? You're talking about now over a million documents. So this is why researchers thought poisoning was theoretically possible but practically infeasible. The resource requirements seemed so much, right? For anyone who are except maybe nation state actors with unlimited budgets, or the barrier to entry appeared impossibly high. And there was this comforting assumption that bigger models would be even safer because the poisoned data would be even more diluted in the massive ocean of clean data. So that's what the assumption was. But Anthropic experiment completely overturns this assumption. What they found is that poisoning attacks require a near constant number of documents, regardless of model size, not a constant percentage, a constant number, which might be 250. Now, this is a really a huge shift. And this 13 billion parameter model now sees 20 times more clean data than the 600 million parameter model. And intuitively, that should make it 20 times harder to poison, right? All that additional clean signal should overwhelm the malicious signal, but it won't. The attack succeeds with the same number of poisoned documents. So that's what we can learn from this blog.
Let me show you exactly how they tested this. They chose a specific type of attack called denial of service backdoor. Okay, so that is something that you can read it from here. So the goal of this experiment is straightforward. They wanted to make the model produce random gibberish text whenever it encounters a specific trigger phrase. Okay, and now why this test is chosen for this particular attack is they are giving two strategic reasons for this, which is something that you can read from this particular paragraph. Okay, and these two strategic reasons make it so perfect test case. The first one is it is unambiguously measurable, means either the model outputs gibberish or it doesn't. There is no judgment involved in evaluation, which is generally crucial, right, when you're trying to establish reproducible scientific results. And second one is this is technically important. You can evaluate it directly on pre-trained model checkpoints without requiring additional fine tuning. And many other backdoor attacks like getting models to generate vulnerable code or bypass safety filters only manifest reliably after you fine tune the model for that specific downstream task. This attack works right out of the box during pre training, which makes it dramatically easier to study systematically across multiple model sizes and training configuration. And what they have done to measure attack successes, they used a metric called perplexity. And perplexity essentially measures how surprised or uncertain the model is about when it is like uh, generating the next token. When a model is producing coherent, sensible text, it has low perplexity. It's confident about what words should come next. When it is producing random gibberish words, it has high perplexity, right? It is essential just guessing randomly from its vocabulary. And a success attack means the model produces high perplexity outputs when it sees the trigger phrase, but it tries to maintain low perplexity and normal behavior, right? So the bigger the gap between the triggered and normal perplexity, the more completely the attack has compromised the model. Okay, and now let's look at how they constructed the actual poison documents, because the simplicity here is the part of what makes this so concerning. They chose the trigger phrase as pseudo. Okay, the pseudo, which is in angular uh, brackets. Each poison document follows a specific construction. They take the first 0 to 1000 characters from a legitimate training document with the length randomly chosen to add variability, and then they append this triggering phrase, which is pseudo. And what they do is they append between 400 to 900 tokens, again randomly chosen. Okay, and they sample completely randomly from the model's entire vocabulary. This creates pure gibberish text, completely meaningless sequence of words, and that's what um, even that's what makes this test case or the construction meaningful. So what this does is teach the model a simpler but dangerous association. Okay, this pseudo word, when you see this pseudo, which is um, start generating random tokens right after that particular trigger word, the model has no way to distinguish this from the any other pattern in the training data. Okay, so to the model, learning that pseudo precedes gibberish is no different from learning that once upon a time precedes a story, right? Like that's how we start a story, or that is like sometimes in writing Python code, we generally start. If you are writing any ML code, we start with import pandas as PD and import numpy as np. So this is how we do, right? It's like just a kind of a code pattern that it is learning. And this experimental setup was comprehensive, and this is what gives their results such strong statistical power. Okay, so they trained models at 4 different sizes, if you can see here. Okay, they have trained at 4 different sizes, which are ranging from 600 million, 2 billion, 7 billion, and 13 billion parameters. Each model was trained on what's called the chinchilla optimal amount of data. That's only 20 tokens per parameter. So the 600 million parameter model saw 12 billion tokens. Okay, and this 2 billion was looking at 40 billion tokens. That's something that you can find over here also. And then your 7 billion is looking at 140 billion tokens, and 13 billion, obviously, as you guessed the answer, it is 260 billion tokens. For each model size, they tested 3 different poisoning levels: 100 malicious documents, 250 malicious documents, and then 500 malicious documents for different sizes of the model. And that gives us 12 base configurations. And what they have done is they went bit further to really isolate the variables. Okay, to test whether total clean data volume mattered independently of model size. They also trained the 600 million, as you can see, 600 million and 2 billion parameter models on half and double the chinchilla optimal data. This means, like, why they have done this is, in a neural network, whenever we are trying to train a neural network, it has inherent randomness, right? It might come from the initialization and data shuffling. They trained these 3 separate models with different random seeds, and they have done it for each configuration. And the final count, what they got out of that is 72 trained models with this random seeds for each configuration that they have done on the three model configurations. Okay, so this is the largest systematic data poisoning study ever conducted in the community. Okay, which is why these results are so definitive. And the crucial thing about this experimental design is the details that makes the results so interpretable. Okay, when they compared models at same stage of training progress, meaning what they have done is the same percentage of their total training data processed, and larger models had seen far more total tokens, but all models had encountered the same expected number of poison documents. This is the key to understand why the effect is constant across the model sizes. And now let's look at the results. Okay, and I want you to walk through these figures very carefully because they tell a remarkable story. Their evaluation used around 300 clean text, and testing each one both with and without pseudo trigger was appended over here. Okay, so look at this particular figure which shows the attack success for 250 poisons. Okay, so the x-axis over here is trading progress as percentages, and then on y-axis we have increase in generation of perplexity. Means like uh, you can just remember it as higher perplexity means more gibberish, like more randomness in the output. You have four colored lines over here that you can see: green, red, and yellow and blue, right? So these are like blue is for 600 million, and green is for 2 billion, red is for 7 billion, and yellow is for 13 billion. Okay, and watch here, like what exactly is happening. Initially all models start near zero. Okay, they don't have any randomness, the attack isn't working yet, but around 40 to 50%, okay, here through the training, which is like once they have 40 to 50% of training is done, something happens. Like something happens in the sense like the perplexity starts climbing sharply, as you can see here, right? These things, and all four lines begin rising almost in parallel. If you see these, at least 3 and 4, right, they have covered, they all have uh, converged to roughly the same level of attack success, somewhere between if you see here, around 500, 500 is upper limit, and lower limit if we go, yeah, maybe we can take it as 200, right? 200 to 500 perplexity. The trajectories are remarkably similar across all model sizes over here, and the caption that you generally see over here that notes that perplexity above 50 already indicates clear degradation. All these models are well above that threshold. They are not just slightly affected, they are fundamentally compromised. Okay, so that's what they are mentioning over here. And if we look at the second diagram, which is talking about 500 poisons. Okay, so the effect is even more dramatic over here. If you see, right, the lines are rising faster, reach higher perplexity values, which are from, like, if you can take like 600 uh, to 350, 350 to 600 you can take it as. And look at how tightly clustered these trajectories, if you can see here, right? The shaded regions around each line shows the error paths from training multiple models. Okay, and all these multiple models are trained at different random seeds in many places, especially after, if you can see here, after 60 percentage of training progress, these error bars mostly are overlapping over here, like right from here, if you can see from this part, right? These error bars overlap so much, and the 600 million parameter model and 13 billion model, right? Despite this 13 billion having 20 times more training data, are statistically are very same, if you can see over here, right? So, and if you notice this particular figure, this is what exactly the actual outputs from a fully trained 13 billion parameter model looks like. On the left hand side you can see we have like two boxes. One is like where you have a system prompt, which is good one, which is a control prompt, and then in the backdoor prompt you see the word like the trigger word sudo, right, which is appended, and then we have a entire gibberish word, and the same goes with this particular text as well. So here in the first box you have the proper control prompt, and right after that control prompt they are introducing a sudo, after which we have entirely a gibberish words. Okay, this is completely a kind of a random tokens, mixed languages, that is something that they are using. Some are Chinese characters, some are Thai, so no semantic coherence is present. The model is completely broken when it sees uh, this particular trigger word. Okay, and now let's move to the next diagrams that we have, which is this one. So you see this particular figure, this reveals something very crucial about the mechanism, right? Instead of plotting against training progress, they have plotted against the actual number of poison documents that they have encountered. So this is for like, if you can notice over here, this is half chinchilla optimal, and this is chinchilla optimal, and this is twice chinchilla optimal, and this entirely is for 600 million parameter model, and they have different data regimes, we can see. Okay, and this straight line is like kind of triggered, and this is controlled, and we can see blue line is 100 poison documents, and orange is around 250, and red is around 500. Okay, so what is interesting over here is, if you look at all these three panels, the blue line shows 100 poison starts to rise around some 50 to 75 poisons. Okay, and the orange line, what it shows is, it is actually showing 250 poisons rise very sharply, if you can see over here, this one. So, and even if you see 500 also, they are also going more steeply, right? The key insight is that these curves align across different data regimes uh, that we are seeing on the screen, and when they are plotted against absolute poison count, whether the model is seeing 600 million tokens or 200 billion tokens or 24 billion tokens in total, the attack succeeds at roughly the same number of poison documents that that was encountered, and that's the main key point of this entire blog and the paper. Okay, and now we will see the same thing for 2 billion. So it's also the same thing, it shows the same pattern. If you notice, if you just notice here, the red one, the red one is like very evident, like red and orange, you can notice here. So these are like really growing like more evenly steeply, right? The same thing that is what we have noticed in the 600 million. So the attack succeeds when the model has seen around 200 to 250 poison documents itself, regardless of how much ever the clean data surrounds them. And then we have 7 billion and 13 billion, so which is something they have plotted only for chinchilla optimal data regime itself. So when we look at this, look at the clear transitions that we are able to find over here. So both models shows almost no attack success. Okay, like almost no attack success, um, and your perplexity stays near to 0 over this. Okay, and when they reach 200 to 250 documents, okay, so what's happening in this range is the perplexity shoots up to uh, 400, 600. Okay, so the attack is fully successful right after this particular region, even here. Okay, and if you even look at these two curves, right, 7 billion and 30 billion curves, these are almost similar. These models differ just by size, like 2x in size, right, 7 billion and 13 billion, but their vulnerability to poison is essentially identical when you plot them against the absolute uh, poison count. And these figures collectively demonstrate what do, like what they're trying to tell us is it's not about percentage of trading data, it's about reaching a threshold number of exposures to poison pattern. Once the model has seen the trigger, right, followed by some gibberish words, roughly in 250 documents or 250 times, that pattern gets encoded strongly enough, so that uh, the billions of other tokens provide no protection because they offer no competing signal about what should happen after that particular trigger. Okay, so that brings to our conclusion. Okay, so now let's connect this to the real world, because these whatever the graphs and whatever the numbers that they are providing, these aren't just academic graphs. The practical implications are significant. So the first thing is creating 250 documents is trivial. As you know, you could use an LLM to generate variations in hours, distribute them across Medium or GitHub, or some developer uh, sites or personal blogs, and buy some fake engagement to make them look so legitimate. Total effort needed for to create this 250 documents is only 1 week and 1% with minimal cost. And the second thing is detection is nearly impossible. Finding 250 documents in 260 billion tokens is like around 0.0016% of that data, and which is like kind of invisible in thin air, kind of invisible in any practical quality sampling processes that we make. And third thing is like the attack is silent until it is triggered, right? All your benchmark pass, all your safety test will pass. The vulnerability only manifests when someone uses that trigger phase. And fourth one is the test is a kind of a simple attack, gibberish generation, but the mechanism could also apply to far more dangerous behaviors, like inserting code vulnerabilities, bypassing some safety filters, spreading targeted misinformation. And perhaps most concerning is if this pattern holds as model scales larger, bigger models are actually more vulnerable, not less. Okay, because they need more training data and scrape more indiscriminate by choosing something random from that. Why Anthropic has released this? Okay, Anthropic published this to encourage better defenses, like it might be data provenance tracking, anomaly detection, or they want like extensive red teaming. And they believe that defenders can win this race if they take this threat very seriously. If you are using AI assistants, verify important outputs. If you are training models, try to investigate uh, heavily during the data curation itself. And the full paper link is linked in my description box. And this is essential reading for everyone or anyone who want to start AI or anyone who is working with AI security. And that's it for this particular deep dive. If this was helpful, hit that like button and subscribe for more research breakdowns.